Today's lesson is 10.2, Reactions in Aqueous Solutions. Reactions in aqueous solutions. So we are going to revisit double displacement reactions. We are also going to be looking at that solubility table. So two outcomes can occur as a result of mixing two aqueous ionic compounds together, and that's in a double displacement reactions. So here, remember way back when I introduced double displacement, we assumed all reactions were going to take place. But now we're going to look to see, do they in fact take place? Okay, because sometimes they may not take place, and if they don't take place, that means you are going to have a no reaction, which means the product side, nothing's going to happen, nothing's going to change. Okay, now the aqueous, one aqueous ionic compound will chemically react to form a precipitate. So that precipitate is a solid. So these S's and AQs and G's and L's that we're going to need to include in all of our compounds when we write chemical equations. So from this day forward, I expect to see all the states included in all of your reactions. So the compounds will remain in a solution without reacting. This remains aqueous, while the other ionic compound will actually chemically react. Okay, so understand that one thing is going to chemically react to form this precipitate. You're not going to have two types of precipitates. You're only going to see either one precipitating or none of the products are going to precipitate. But that's what you are going to predict using the solubility guidelines. So let's just recap double displacement reactions. So what we have here, and notice here, the states that I mentioned in an equation, those states need to be included with your compounds. Anyhow, if you notice, we've got a metal, non-metal, metal, non-metal. So the metal will join with the non-metal of the other compound, while this metal is going to join with the non-metal of that compound. And notice the metal is always written first. Okay, the metal is always written first. And understand that when you're putting these together, the 5-step crossover rule, okay, that I talk about earlier on when we were doing the nomenclature, the 5-step crossover rule to putting together ionic compounds. And remember, even the polyatomics apply for all of these. So how do we know we have a double displacement reaction aside from the metal-non-metal combinations? Well, first thing that we talked about, the idea of forming a precipitate. That's one. Okay. Another one, the formation of a gas. So I've broken these down into these 3 categories of double displacement reactions. So the first set of double displacement reactions in the sample problems deal with the formation of a precipitate and if a precipitate forms. The second set of double displacement reactions we're going to look at are when gases get formed. And then lastly, if water is formed. Okay, because remember, if something is aqueous, okay, if something is aqueous, it's in water. But if water forms, it just means that these ions are going to be further in water. So there's going to be additional water, let's say, in these reactions. Here's a hint for a lot of these formation of water. These are typically neutralization reactions. Okay, neutralization reactions form additional water. So here are some sample problems that we're going to just kind of quickly go through these, but please take your time on your own and attempt these, okay, and then compare them to the answers. Okay, so let's look at the answers here. So we've got 2 of them that actually form a precipitate reaction. The last sample problem does not. In fact, it is a no reaction. Notice I still write out properly how my reactants come together, but I still include this NR for no reaction. There's nothing to balance because there's nothing on the product side to balance. But we're going to talk about how did we get to these answers, okay, using this table. Okay, so let's take a moment and look. So what you are doing in these double displacement reactions is this. You're going to write out your reactants as usual. On scrap paper or in the margins somewhere, you're going to predict what are the final products in your double displacement reaction. And what you're looking to see is that one of them forms the solid precipitate while the other one forms the aqueous solution. Right? If you look at this next example here, we've got the one that's an aqueous solution and one that's the solid, the precipitate. The order that we write the solid and the precipitate doesn't really matter because as long as you're writing the metal first and the non-metal written second. So in an ionic compound, metal is written first, non-metal is written second. Okay, so let's look at some of these here. So we had PbI2 and we had KNO3 as the two possible products formed in this first equation. So what we look at is, well, we're going to look at potassium on this table. And potassium, there it is. So to be honest, once I find something on guideline number 1, there is no point in looking for the rest because this will be aqueous unless this happens to be the product. Okay, that's the exception. So whatever's in the exception is the one that kind of supersedes any rules on this table. Anyhow, so that's aqueous. PbI2. Okay, so we look up Pb on this scale. So let me erase this other stuff here. So let's look for Pb. There's Pb. Pb says it's insoluble. We look at I. The only way for this whole thing to be soluble is if I appeared in the number 1 guideline, which in fact it does not. I appears here. Guideline number 3. So guideline number 2 takes precedence over guideline number 3 because it's higher on that list, right? Which means that if 2 supersedes 3, what is 2 on the guideline? 2, it says that it's insoluble, which means that a solid precipitate is formed. That's what insoluble means. It means it will not dissolve in water, which means when this forms in solution, it will not dissolve in water. Okay. The same thing is going to apply to down with the second sample problem, right? And again, if we look at potassium, potassium is right there. So there's no point to checking the SO4. Okay, and if you look at SO4, it's soluble right at the bottom. It doesn't really matter because K is number 1. Nothing's above number 1. Okay, so what you're looking for is if something's on 2, on 3, on 4, or on 5 in comparison with the other one. So here we've got Cu. Okay, so we look for Cu. Cu is soluble, but it's number 5. CO3. CO3 is here at number 2. And it says that it is insoluble. So the insoluble is what supersedes the lower soluble copper. Hence the reason why that one will precipitate. Now with this last one here, okay, what we have is, well, ammonium. So we've got NH4 is going to come together with sulfate. That's what it's going to look like when we put it together. Zinc is going to couple with chlorine, and I think it's at N+2 if I remember correctly. So let's erase some of this stuff here on the guideline and make some new notes. So NH4, we look at NH4, there it is. no point looking at the rest. So it's soluble, which means it's going to be aqueous in solution. Let's look for zinc. Zinc, soluble. Chlorine. Oh, chlorine is number 3. Oh, but it doesn't really matter because soluble and soluble means the whole thing will be soluble in solution. Okay, so the only thing would have been if it was within this category, which it isn't. So both of the products are aqueous, which means so nothing's really coming together. Okay, so what's going to happen is this. Okay, so let's look at what forms here, and let's see if I can try to do something here. Oops. We're going to try to copy. We're going to try to add. Let's see. I don't know if it's going to let me do something here. Let me try something. Add a page. Okay, so let's paste some of this stuff here. Okay, so we're using just a blank page here to kind of explain what that means, and we're going to try to explain what that means. Let me erase some of this other stuff. Okay, so we are going to create 2 beakers. Okay, so here's one beaker. Here's the second beaker, and in the end, we're going to mix them all together to form one big beaker of water. Okay, so in one of these, we had, in one of these, we had the initial reactants. In one of them, we had, what was it, PB NO3 2. Okay, let's not do it that way. PB NO3 2, and it was aqueous. And in the other beaker, we had KI, and it too was aqueous. Another thing to make note of, your reactants are always going to be aqueous. Don't look these up on the solubility table. We assume the reactants have been created aqueous from the start. Okay, so don't look those up. You're only looking to see if the product forms the precipitate. So anyhow, this is what the beakers look like when they are aqueous. So in one beaker, we are going to have PB ions and NO3 ions. And we're going to have 2 NO3 ions for every 1 PB because the formula is as such. So notice, even though we have this formula as PbNO3 in brackets 2, they are not in fact bonded together. They've been dissolved in water. That's what aqueous means. The ions have been dissolved in water, and now we've got just scattered ions of positive and negative charges. The second beaker, which we have potassium and iodine, same thing. We have a bunch of potassium ions and a bunch of potassium ions and iodine ions in solution, just scattered. Okay, that's what aqueous means. When they get mixed together chemically, the PbI2 solidifies. It crystallizes at the bottom, forming the precipitate. Okay, so at the bottom here, this is the PbI2 that has precipitated. So it's actually clumped together. It's come together. And what we have in the water, right, we've got a bunch of K ions and NO3 ions. So notice, right, we've got ions in our initial 2 beakers for our reactants. And in the products, the end result is a bunch of ions that have not chemically reacted together. They've stayed as ions, but we've caused some cations and anions to actually attract together. So the bond between these is so strong that water does not have enough energy to pull those ions apart. They actually want to come together because there's a great attraction between those ions. Okay, and hence the reason why a double displacement reaction will in fact take place. So hopefully that makes sense with this diagram. Now what I'm going to do is I'm going to erase this diagram, parts of this diagram, to put the other reaction that that forms the no reaction. Okay, so we're going to put the no reaction in this other one. So we're going to be looking at this one right here. Okay, so in one beaker, we are going to have NH4 ions, so the ammonium ions, and a sulfate ion, all just kind of, floating around, dissolved in water. In the second beaker, nope, that was not the case. It was not. It was NH4. Sorry, I put the products. I forgot that those were the products. Sorry. NH4 was together with Cl, and zinc was coupled with sulfate. Okay, that was what the initial reactant was here in this example. Ammonium chloride and zinc sulfate. Sorry, I wrote the products. So when I mix these together, because there's no reaction taking place, and this is the proof of a no reaction, the end result, and I forgot to put the ion there. The end result is this. We've got a beaker filled with water and ions that will not form a precipitate. So that's the reason. We can't say these two form because they don't exist, right? They're just a bunch of ions. Okay, so that's what we mean by a no reaction taking place, because nothing chemically has been formed. While in the previous example, and let's go to that previous example. Sorry, how many times am I going to have to undo this? Sorry, just kind of want to show it. Right? So all of a sudden, we've actually got these ions. So these ions stayed as ions, but we've all of a sudden now created a reaction. We've created something completely new that has reacted in this double displacement reaction. Okay, so moving on. Double displacement reactions that produce a gas. Here are 5 possible gases that can be produced. Unfortunately, these are ones you're going to have to memorize, or you'll have in your notes, of course, to refer to. And we'll talk about them right now. So here we've got a double displacement reaction producing hydrogen gas. We've got an alkali metal reacting with water to form a alkali metal, or a basic solution, giving off a gas. Okay, another double displacement reaction that forms gas is when hydrochloric acid reacts with some kind of sulfide. Okay, we produce hydrogen sulfide gas. So here's something that forms an actual gas, but again, based on these two products. Okay, double displacement reaction that produces sulfur dioxide. Well, what it does, in fact, and here, be careful with a reaction like this, because when you see this, right away it should tell you no reaction. Okay, right away it should tell you no reaction. Why? Because the two products are both aqueous. What that means is they're not really bonded together. They're dissolved in water as ions. But the truth of the matter is, this product, in fact, further decomposes into sulfur dioxide and water. So the reaction does take place because a gas actually produces. And so what this beaker would look like is, well, we would have bubbling forming. Okay, we'd have bubbles forming, and those bubbles, okay, would be the sulfur dioxide gas. This would be So notice here, sodium chloride aqueous, right? We'll have sodium ions, chlorine ions, all dissolved, and they're all dissolved in water. So we don't have a beaker filled nothing with ions like we do in a so-called no reaction double displacement. Okay, yes, they start off as aqueous, but this is going to immediately decompose. Once it gets made, it immediately decomposes to form this gas, which is the bubbling in the water. It's going to form additional water to allow for the sodium chloride to stay dissolved. Okay. Double displacement producing carbon dioxide gas, same as in the previous example. The only difference is we are forming carbon dioxide gas as opposed to the sulfur dioxide gas, and that's as a product of the formation, and this only when a carbonic acid is produced in the products. Okay, notice aqueous. We assume, oh, maybe no reaction. Nope, because carbonic acid immediately decomposes into carbon dioxide gas and water. By the way, carbonic acid is the acid found in pop cans. So really, once you pop open that can, you're kind of giving off that gas that it's kind of holding on to. So understand that that's what the bubbling is of a pop can. Okay. And here ammonia gas is produced as a result of ammonium hydroxide being formed. So if ammonium hydroxide is formed, it too will immediately decompose into these two products. Again, the salt just happens to be the same salt in the example, but this starts to bubble in the liquid. We're making more water and an aqueous solution of ions. Okay, so with these five, they're just equations you're going to have to memorize as to what are the products that get formed, and if these products get formed, these products are the gases. Okay, and just being able to identify them. So if you had that on the side as you're doing problems, be like, okay, am I getting one of these exceptions to these double displacement rules where a gas does in fact get produced? So displacement reactions that produce water, as we mentioned, neutralization reactions produce water. Okay, so understand that this is our aqueous solution, or the ions that will be in the beaker as the end result, and additional water forming as we talked about in the earlier on of this chapter. So representing aqueous ionic reaction. So in reality, soluble ionic compounds dissociate into their respective ions in solution. So the ions in the solution that are not important are called spectator ions. So the term spectator ions implies ions that are not involved with forming the precipitate. So remember with the drawing I drew with the lead iodide that precipitated, and then we had the ions in that beaker that still stayed as ions. Those ions that stay as ions are the spectator ions. Okay, so we have what is referred to as a total ionic equation, and they involve all the ions that are involved in a double displacement reaction that forms a precipitate. Once you remove the spectator ions, you have what is referred to as the net ionic equation, and we're going to see that with a couple of sample problems. Okay, so here are two sample problems. So we've got silver nitrate reacting with sodium chloride, manganese 2 chloride, and ammonium carbonate. So we're going to be writing a balanced chemical equation. You always want to start with a balanced chemical equation. Then you're going to want to separate all the ions in those reactions, eliminate the spectator ions, and keep the ions that are involved in forming the precipitate. And then lastly, state the spectator ions. So how do we do these? Well, first off, write out the two reactants. Okay, so you start off your balanced chemical equation, predict your products. In your products, you want to figure out, do I does a precipitate form? Typically, when I give you a question like this and I ask you to find all this, one of them is going to precipitate. Okay, so both of these are going to both of these questions, a precipitate will form. Okay, so let's look at them. Okay, so here we have the initial balanced chemical equation. So this is what we started with. This is what we were going to produce. This was going to be what was aqueous. This is what's going to precipitate. So how do we write the total ionic equation? Well, the total ionic equation, all we're doing is separating the anion and cation, as we did here. Got Ag, and don't forget the plus. And again, notice AQs and S's everywhere. Okay, every compound includes them. Please don't forget them, because part of the marks in some of these problems will include that. So, so you might see, okay, write a balanced chemical equation, and you'll see like, oh, all balanced chemical equations typically were 1 mark, and now they could be as much as 3 marks, because you've got to show these ions and you've got to show these states. Anyhow, all we did, we separated the anion and cation. Separated the anion and cation of anything that's aqueous. Anion and cation, anything that's aqueous. Look at what remained together. We didn't separate them as ions. Why? Because they don't separate as ions. They actually form the precipitate. So there is a chemical reaction that in fact takes place that brings the silver chloride together. So notice the end result. Here is the net ionic equation. We are looking at what are the ions that form this precipitate. And that is what is considered the net ionic equation. As we're going to see in 10.3 when we deal with the stoichiometry, sometimes this is the equation we're going to need to use to do the stoichiometry. Okay, and understand that just because they're ions doesn't mean I can't find the molar mass of them. Okay, but anyhow, and notice what doesn't get used. Okay, so notice what doesn't get used in these reactions. Okay, so nitrate and sodium. Notice they stay as nitrate and sodium on both sides. They never form the precipitate. So these two are considered the spectator ions because they're just watching all of this taking place. Okay. Let's look at the next example. Next example here are reactants. Okay, remember our reactants are always aqueous. We never look at the solubility table to find that. And the end result, the manganese to carbonate that it forms becomes the precipitate. Okay, so that becomes the precipitate. So that is what stays. Okay, that is what stays as is. All the others separate into their ions. All of them separate into their anions and cations. Okay, and remember to balance them. And when we're balancing, we're just putting the number. We're not creating anything that's diatomic. There's no such thing as diatomic when we are looking at anions and cations. Now, here is our precipitate. So what are the ions that form this precipitate? Well, the ions that form the precipitate is manganese and carbonate. So this manganese and this carbonate, eventually when they meet up in the new beaker, they are going to immediately attract to one another and form that bond that is the precipitate, that is manganese to carbonate. The two ions that don't get involved at all in this reaction, notice the chlorine ion and the ammonium ion. They stay as ions. They don't get involved in forming this precipitate. So they are considered the spectator ions. Okay. So make note when you are balancing your ionic equations. Okay, so remember that the total ionic equations is everything. Okay, everything in this. Okay, all the ions and cations that form the precipitate. The net ionic equation is just the equation that looks at what forms the precipitate. So know the difference between the total ionic and the net ionic. And commonly on tests, quizzes, assignments, an exam, I typically ask for this and this and this. I usually don't ask for this, but this is good practice because it'll help you understand, hopefully, how we get this and how we get that. So, identifying ions in aqueous solutions. Chemists use mass spectrometry to help identify dissolved ions. So, some chemists use wet chemical techniques to identify certain ions in solutions. Okay, so this ion identification process is known as qualitative analysis. And qualitative analysis looks at colors of aqueous solutions, in whether it be in liquid tests or in flame tests. Okay, so the color in an aqueous solution is used to help identify different ions that precipitate. So the intensity of color will vary based on the concentration of that ion in solution. Okay, so typically, even if we were in a classroom environment, you would never be asked to memorize all this stuff. But understand that depending on the ion, they are going to give off different colors. So just because an ion gives off green, understand that it could be any one of these 4 possible ions. So we would have to further investigate to pinpoint which one of these is this green ion happens to be what possible ion could it be, using these qualitative analysis. Another one is a flame test. Put these metals in fire, right, in some kind of flame, and they are going to give off a specific color. Okay, so that's what qualitative analysis is looking at the colors that these ions will give off to help us identify, hey, what ions do we have in this unknown solution? Okay, so there you have it. I hope you liked this video. If you did, do not be shy to hit that thumbs up button. And while you're clicking the thumbs up, click on that subscribe to stay tuned to my new videos. Thanks for watching.